NEX, a high-performance decentralized trade and payment platform. Ethan Fast, Ph.D. Neon Exchange Stanford, CA, USA. Ethan at neonexchange.org. Fabio C. Canizan, MSc Neon Exchange Cambridge, MA USA. Canizan at neonexchange.org. Luciano Engel, Eng Neon Exchange Florianópolis, Brazil. Luciano at neonexchange.org. Fabian Wall, Ph.D. Neon Exchange Zurich, CH. Fabian at neonexchange.org. Thomas Saunders Neon Exchange Minneapolis, MN, USA. Tom at neonexchange.org. Abstract today. Cryptocurrencies are primarily traded on centralized exchanges where user funds are at risk to hackers and platform managers. Decentralized exchanges, DEXs, allow users to retain control of their funds as trades are mediated by smart contracts on a blockchain. Unfortunately, today's DEXs are slow, hard to use, and are restricted to trades on a single blockchain. Neon Exchange, NEX, is a new decentralized exchange that solves these problems, leveraging a high-performance off-chain matching engine built with Elixir to handle massive order volume, allow cross-chain exchange, and support more complex trading APIs. Many people do not use DEXs because they cannot trade with their national currencies. NEX is the first DEX that will allow its clients to enter the exchange with fiat currencies such as USD, powered by a global network of licensed third parties. Exchange services are critical not just for users of cryptocurrencies, but also for many other applications built upon blockchain technology. NEX envisions a vibrant ecosystem of web-based decentralized applications, DApps, running across public blockchains such as Neo, Bitcoin, and Ethereum. These applications require tools to interact with, make transactions upon, and send data across chains. To achieve this vision, NEX is developing the first cross-chain browser extension. Web applications can use this extension to collect payments for goods in any digital currency, make trades and transactions across blockchains, and interact with smart contracts across Neo and Ethereum. All of this cross-chain functionality is powered and made possible by the NEX off-chain matching engine. NEX is issuing 50 million tokens to fund development and future expansion, of which 25 million will be sold to the public. NEX tokens are in the process of being registered as a security, first in Europe, and will provide holders with a share of all revenue generated by the exchange and related services. Revenue per user will be determined by the number of NEX tokens they hold and the length of time they commit to staking their tokens. The minimum fee share rate is 25%, increasing linearly to a maximum of 75% when tokens are staked for 2 years. Computer Science Ph.D. to be granted in May 2018 by Stanford University. Version 2.0. Copyright of Neon Exchange, 2017. 1. Introduction. Cryptocurrency markets have grown enormously in recent years, from a daily trade volume of $60 million in January of 2015 to more than $8 billion in November of 2017. 2. Despite the fact that most cryptocurrencies are secured by decentralized architectures, almost all trades between currencies take place on centralized exchanges, where funds must be deposited under the control of the entity facilitating exchange. This layer of centralization puts user funds at risk. To contract might accept incoming funds from a user, then release them at a certain date, or collect funds from a series of users and split them evenly. These smart contracts are what make possible more sophisticated distributed on-chain applications such as decentralized exchanges. 2.2. Decentralized exchanges. Many decentralized exchanges have emerged over the years. In this section, we lay out the trade-offs in this design space, and how NEX contributes over existing systems. In summary, NEX trades a small degree of user trust for vastly improved performance and usability. The earliest decentralized exchanges placed order books directly on the blockchain. 4. In these systems, market makers must perform on-chain transactions every time they want to place, modify, or cancel an order. Further, as new orders are placed, a smart contract must execute matching logic that runs slowly and redundantly on all virtual machines in the network. In general, these exchanges take up a large amount of network bandwidth and operate very slowly, so very few decentralized exchanges operate under this scheme today. A second class of systems uses automated market maker, AMM, smart contracts, as opposed to an on-chain order book. 25. These systems adopt a price adjustment model, where all parties trade with the AMM, and the spot price of an asset is determined by the resulting market forces. While AMMs provide increased availability and performance over on-chain order books, They are still much slower than centralized exchanges and must place artificial constraints on supply to prevent their working capital from being depleted by potential arbitrageurs. State channels have been proposed to reduce network overhead for the more general problem of asset exchange. 22.6. Allowing two parties to iterate on a transfer off-chain before ultimately committing to it on-chain. However, state channels are expensive to open and close, usually requiring a security deposit and a series of on-chain transactions. For this reason, they are most useful among known parties who want to manage a series of interactions. For example, a bar tab, not a single party conducting one transaction with a broader market, building from state channels. A more recent class of DEX is based on off-chain relay. 28.3. In these systems, market makers broadcast an order off-chain, which can then be picked up by an interested counterparty and passed to a smart contract for fulfillment. These systems require far fewer on-chain transactions to perform a trade, but still suffer from performance issues in comparison to centralized exchanges. Notably, order matching is not automatic in these systems, presenting arbitrage opportunities against users who are slow to cancel their orders. Similarly, the absence of matching means that users cannot place more complex orders such as limit buys or market sells. In contrast to these approaches, we introduce a new kind of decentralized exchange, NEX, based on a trusted, off-chain matching engine. This matching engine works exactly like its equivalent in a centralized exchange, but only has control over active orders, and commits trades on-chain without access to the full balance of a user account. Like exchanges based on off-chain relay, NEX orders are matched off-chain and fulfilled on-chain, but NEX's automatic matching engine reduces opportunities for arbitrage and allows for more complex orders. To ensure trust, NEX provides a public record of orders and a deterministic specification of behavior, so that users can verify orders matched off-chain and claim an award in the event of incorrect behavior. Taken together, this makes NEX the first decentralized exchange with performance comparable to today's centralized exchanges. 2.3 Cross-chain exchange. Cross-chain exchange is the process of trading or transferring assets that exist on two different blockchains. For example, trading NEO for ETH. This kind of exchange is trivial when two parties trust one another or an independent third party. For example, a centralized exchange. However, exchange becomes much more difficult in the general case, where trust is absent. As a simple example, if one person sends ETH to another in expectation that the other will send them back NEO, the second party may simply keep the ETH transferred by the first without fulfilling the exchange. Atomic swaps offer one approach to facilitating cross-chain trades without trusting a third party. 18. These swaps make use of hash-time-locked contracts, HTLC, a multi-signature transaction scheme that requires cooperation from both parties for a trade to be successful. While this approach has seen several successful implementations, 19. It is in practice a slow and cumbersome process that is not suitable for a high-volume exchange. Atomic swaps require potential traders to first find each other to coordinate the swap, then engage in multiple transactions on two different blockchains. Other projects have proposed cross-chain relay as a more scalable approach to decentralized cross-chain exchange. 24. In this approach, smart contracts on one chain are given the ability to verify transactions on another. For example, NEO smart contracts might be provided with a stream of block headers that would allow them to verify transactions on Bitcoin. Given such a setup, a smart contract could tell when a transaction has occurred on another chain and so unlock funds on its own chain. Unfortunately, this approach requires trust in an oracle that provides information about the external chain and cannot be fully implemented on chains without smart contracts, such as Bitcoin. In contrast, we introduce a new approach that simplifies cross-chain transactions, though a small trade-off in trust. Because the NEX matching engine is off-chain, it can easily act as a coordinator and intermediary between many separate chains. For example, if user A wants to trade 100 NEO to user B in return for 10 ETH, the matching engine can delegate fulfillment between smart contracts on both NEO and Ethereum. On NEO, one smart contract will move 100 NEO from A's address to B's address, while simultaneously on Ethereum, a similar smart contract will move 10 ETH from B's address to A's address. As with all trades matched by the engine, NEX provides a public record of orders and a deterministic specification of matching behavior, so users can verify the correctness of a cross-chain match and claim a bounty in the event to incorrect behavior. 2.4 The NEO blockchain. NEO was launched in 2015 as China's first public blockchain. 31. NEX will run first on Neo, before later expanding to support exchange on Ethereum and other blockchains. While most of the ideas behind NEX apply to both platforms, there are several major differences between Neo and Ethereum that are relevant to decentralized exchanges too. 4. 1. Modeling user balance. Ethereum is based on an account model, where a user's balance of ETH is stored as a number in the Ethereum virtual machine, EVM, and can be easily modified. For example, sent or received by smart contract logic. 12. In contrast, global assets in Neo such as Neo and Gas are based on a UTXO model, where funds are sent and received through a chain of spent transactions on the network. 10. Notably, these differences only apply to global assets on the Neo network and not tokens created through smart contracts, which behave similarly to ETH. 13. Each system design has trade-offs. In Ethereum, for example, it is easy for a smart contract to interact with the user's balance of ETH, but difficult for a node to prove that a transaction has taken place without syncing the full chain and running the EVM. In contrast, it is easy for third parties in Neo to verify that a transaction has taken place on the chain, for example, through SPV. 9. But much more difficult for smart contracts to program interactions with the user's Neo or Gas balance. For NEX to succeed, smart contracts on Neo require some way to programmatically interact with global assets like Neo and Gas. To solve this problem, we introduce a novel token representation smart contract that converts global assets into smart contract tokens, which can then be easily interacted with by smart contracts on the Neo network. Users can convert their global assets into tokens by depositing them at the smart contract address, then later withdraw them from, perhaps with a different balance, whenever their interactions with the third-party smart contract have been completed. We believe this solution will generalize to other networks that combine UTXO models with independent smart contracts, such as Cardano. 7. 2. 4. 2. Consensus. Neo and Ethereum also operate under very different consensus models. Neo uses delegated Byzantine fault tolerance, DBFT, for consensus, 2027, whereas Ethereum uses proof of work, POW. 8. Neo's consensus model allows for higher theoretical transaction throughput, which has a positive impact on the performance of a decentralized exchange. Neo consensus also provides finality. Once a block has been generated by consensus, it is not possible to have competing version of the chain within the network. As Ethereum moves to a proof-of-stake (POS) model in 2018, for Neo's comparative advantage may diminish, but many details have yet to be worked out before that transition occurs. 14. 3. Neon Exchange. NEX aims to combine the performance of centralized exchanges with the trust and security properties of decentralized exchanges. The system consists of three main components: an off-chain trade matching engine, a smart contract where trades are executed, and a payment service where global assets such as Neo and Gas can be converted to tokens that can be transferred directly by smart contracts, making them compatible with the exchange. In the following sections, we describe each component in more depth. 3.1 Off-chain matching engine. An off-chain matching engine allows NEX to benefit from the performance characteristics of centralized exchanges, while maintaining a decentralized user account model based on the blockchain. Figure 1. Orders are signed and sent from user addresses to the matching engine, where they are quickly and deterministically processed using high-performance hardware. Match stored concretely. Matching on NEX occurs deterministically based on price and time, commonly known as FIFO. 15. Lower-priced orders will be matched first, with preference given to orders placed earlier in time at a given price level. Any modifications to an order will reset its placement time. 3.3 User accounts. The security problems of centralized exchanges are not simply a technical challenge to be overcome, but also a social consequence of the common user desire to hold assets in exchange accounts. This desire is largely due to the familiarity of the bank-like user experience provided by these centralized platforms when managing funds. NEX aims to bring a similar user experience to decentralized exchange by storing a user's encrypted private key client-side in a user's browser. This preserves the security guarantees of a decentralized account model while allowing users to log in into NEX through a traditional web form that asks for a username and password. 3.4 National currencies. One major problem with today's decentralized exchanges is lack of support for national currencies such as USD. NEX is solving this project through banking partnerships with companies around the world. Through this network of partners, Users will be able to buy cryptocurrencies directly using national currencies to store in their wallets and trade on the exchange. 3.5 Types of orders. Unlike existing decentralized exchanges, which only support point-to-point orders that allow tokens to be traded at a fixed price, NEX supports more complex trades such as limit and market orders. Below we describe the types of trades available in NEX. Table 1. Table 1. Order types supported by NEX. Type description: limit exchange tokens above or below a given price ratio. Market exchange one token for another at the current market price. NEX is able to support these complex order types due to the speed and flexibility of its matching engine, which is not limited by slow computation cycles on the blockchain. 3.6 Exchange API. NEX exposes a public JSON API that third-party applications can use to trade tokens. This API allows users to place, modify, and cancel orders on the matching engine. Because these transactions take place off-chain, the NEX API can handle tens of thousands of requests per second, in line with popular centralized exchanges. 16. To submit an order to the matching engine, a client must make a JSON request that is signed with the private key associated with the address placing the order. This ensures that a user cannot submit a trade on an address they do not control before attempting to match an order. The engine will also verify that the user has granted NEX's smart contract enough of the asset such that the order can successfully be executed. If the user has not authorized enough funds, the order will be rejected. To modify or cancel an order, a user must similarly submit a JSON request signed with the correct private key. An order will then be cancelled or modified if it has not already been matched. If an order has been partially matched, then only the unmatched portion of the order will be affected. 3.7 Fee structure. NEX follows the maker-taker fee structure common to other exchanges. Market makers who place new limit orders on the order books will pay no fee, while takers who place an order at marketplace, or a limit order below the current market price will pay a small fee. Table 2. Fees will be deducted from the taker in the token denomination of their trade. NEX computes a user's 30 days moving 6. Table 2. NEX initial fee structure: user 30 days, volume taker fee, maker fee 0%, 0.25%, 0%, 1%, 0.22%, 0%, 2.5%, 0.19%, 0%, 5%, 0.19%, 0%, 10%, 0.16%, 0%, 20%, 0.13%, 0%. Average volume using the volume of trades associated with their public key as a percentage of total exchange volume. 3.8 Implementation: the NEX off-chain matching engine will be built in Elixir, a functional programming language designed to build scalable, distributed, and fault-tolerant applications. Elixir builds on top of Erlang, a language originally intended for development of telecommunication systems, which is now used by modern web developers to manage the challenges of dealing with high availability. Elixir will help NEX realize an off-chain matching engine that provides service to users from all over the world, while functioning continuously and without downtime. 3.9 Smart contract for token exchange: the NEX matching engine communicates with a smart contract that commits trades between users. This smart contract contains logic powered by the NEP5 token standard, which allows it to hold to user tokens involved in active trades. Once the matching engine computes a match, it sends this smart contract all involved user addresses and the types and amounts of tokens to trade between them, and the contract completes the trade. Calls to this smart contract can be batched in a single invocation transaction to increase performance and reduce network volume. 3.9 One trade method signature: the NEX exchange smart contract (SC) accepts two parameters: a string indicating the operation to be performed and a byte array containing serialized data for usage in the method. The output of any call will be returned as a byte array, with the first byte indicating the success or failure of the call and any resulting data serialized in the remainder of the byte array. The central interface between the off-chain matching engine and the blockchain will be the trade method of the exchange SC. This method will take the parameters currency maker, currency taker, amount maker, amount taker, address maker, and address taker. With these data, the exchange SC delegates the trade of each currency to a corresponding SC via the NEP5 transfer from method. In the case that the transfer of currency from the maker to taker or vice versa fails, any non-failed transfers will be reversed and the method will return false. Otherwise, the method will return true. To ensure that no third party can execute a fraudulent trade between users, the trade method of the exchange smart contract will only accept orders signed by a private key held by the matching engine. 3.9 To withdraw, the NEX smart contract only has access to funds involved in active trades, and not the full balance of tokens at a user's address. To retrieve tokens held for an active trade, a user can submit a cancel order to the NEX matching engine, which will then submit an immediate withdrawal order to the exchange SC, transferring tokens back to the user. Delegating this request through the matching engine ensures that the engine will not match an order that is no longer backed by user funds. However, to enhance user trust in NEX, the smart contract also supports a slower direct withdrawal that requires no communication with the off-chain matching engine. This second withdrawal process ensures that 1. Users can withdraw active trade funds in the event of a broken or compromised matching engine. 2. The matching engine has enough time to notice and cancel orders invalidated 7 through any direct withdrawal of funds. To withdraw directly, a user first calls a public withdrawal method on the exchange SC, specifying the token type and amount. 10 blocks later, the user can then call a complete withdrawal method, and the tokens will be transferred. Users can always retrieve funds immediately by submitting an order cancellation to the matching engine, so we expect that the slower direct withdrawal method will not often be used. It exists simply to prove that users control any funds involved in active trades. 3. 9. 3. On-chain settlement. Even with batched trades and a blockchain with high TPS, on-chain settlement will occasionally be too slow to keep up with the off-chain matching engine. To combat this problem, we adopt a multi-user state channel approach. The matching engine keeps track of user account balances in memory as these balances are updated via trades that come in over the API. Periodically, these balances will be committed back to the chain in settlement. However, because funds committed back to the chain may need to be reused for new trades that come in over the API, it is not sufficient to simply settle these balances directly back to a user's account. For example, suppose a bot trades some Ethereum for NEO. In a naive approach to settlement, as soon as the NEO is settled in the bot's account, the bot would have to reauthorize the funds to the matching engine to commit a new trade, which would require at least one new block to be created on the chain before the funds would be available again. This would prevent the bot from quickly reacting to new market conditions and, for example, trading the NEO back to Ethereum at a higher price. To solve this problem, we have created a smart contract vault that can be accessed by both the bot and the matching engine for future trading. So, when a trade is committed, a bot can elect to have the funds move back to the vault instead of its own address. There, the funds can be traded again immediately by the matching engine with no delay, even before the funds have been committed to the vault. At any future time, the bot can remove the funds from the vault with several blocks of delay to warn the matching engine and avoid committing impossible trades. These vaults can be created on both Ethereum and NEO to support trades between any combination of NEP5 and ERC20 tokens. Figure 2. Cross-chain exchange on NEO and Ethereum 3.10. Cross-chain exchange. To enable cross-chain exchange, the matching engine coordinates settlement across two chains simultaneously following the procedure outlined above. To do this, the engine simply tells smart contracts on each chain where to move the funds that have been allocated for trading. Figure 2. The matching engine is off-chain and so can communicate with smart contracts on any number of chains. Further, every NEX user will own an address on each chain operated on by the exchange. Example: suppose user A wants to trade 100 NEO for 5 ETH, and user B wants to trade 5 ETH for 100 NEO. Each user places a limit order on NEX, moving their funds into smart contract vaults on NEO and Ethereum respectively. When the matching engine matches the trade, it sends a signal to the vaults on each chain. On Ethereum, the smart contract moves 5 ETH into A's address, while on NEO the smart contract moves 100 NEO into B's address. 3.11 Withdrawal for UTXO-based assets. While smart contracts are not able to directly transfer UTXO-based assets such as NEO or gas to a user address, they are able to execute logic that decides whether a user is authorized to withdraw a certain amount of these assets through a normal contract transaction. We use this idea to allow users to withdraw funds from the token smart contract. Concretely, to withdraw a UTXO-based assets, a user calls the withdrawal method on the service SC, specifying an unspent TX ID, asset type, and the amount to withdraw. The smart contract checks this information, and if a user is cleared for withdrawal, adds the TX ID, output address, and amount to a whitelist in VM storage. This whitelist is consulted in any attempted transfer of funds from the smart contract. The user can then withdraw the appropriate amount from the smart contract using a normal contract transaction on the network. By default, This kind of withdrawal is a two-step process. In the first step, a user registers a TX ID and amount in the system for withdrawal, and in the second step, they perform a contract transaction to execute the withdrawal. However, it is possible to make withdrawals a one-step process from the perspective of an end user by incentivizing third parties to perform the second step of the process, allowing them to take a small gas fee. In this scenario, a user would authorize a withdrawal with the SC, and a number of bots monitoring public events on the chain would compete to execute the contract transaction in return for the fee. Figure 3. The NEX web extension allows browsers to communicate with and across blockchains. 3.12 NEX web extension exchange is a key component of user interactions with an ecosystem of decentralized applications. For example, users may want to make payments to a website using blockchain-based assets, convert assets on demand to meet the needs of a specific service, or interact with smart contracts on one blockchain using assets from another. To make possible these interactions and many others, we are developing the NEX web extension, the first browser extension to manage assets across multiple chains, allowing web-based dApps to interact with assets through a consistent API. Figures 3, 4, 3, 1, 2, 1 Asset Management. The NEX web extension provides users with a full-featured cryptocurrency wallet with the ability to view asset balances and transaction history, and send and receive assets. The wallet will initially support NEO and NEP5 tokens, before expanding to ETH and ERC20 tokens. In addition to these standard features, the extension will allow users to monitor ongoing trades on the NEX platform and convert balances between cryptocurrencies. The extension will also allow users to purchase cryptocurrencies with national currencies, for example, USD, from partnering banks. 9 Figure 4. The NEX web extension provides asset management software that can interact with web pages within a user's browser. 3.12 2 Extension Web API. By building tools for blockchain and cross-chain interaction into a single web extension, NEX will allow decentralized websites to interact more seamlessly with users through several APIs. User identity. Websites can leverage the web extension to pull and populate relevant user information into a page, for example, a user's NEO address, or the address of a contact. For security reasons, this information will only be available after a user has specifically approved a domain to access it. Transaction initiation. Websites can initiate transactions through API calls to the web extension, resulting in a new extension window pre-filled with the relevant transaction data. This is useful, for example, in shopping websites, allowing for one-click purchases after user approval of a transaction. Smart contract invocation. Some websites may integrate information from smart contracts. This API allows such websites to initiate a call to a smart contract in a new transaction window. 3.12 3 Security. Security is vital when building any asset management platform. The NEX extension has undergone a full security audit by the Cure 53 team. 1. The extension also integrates security features to prevent spoofing, such as a secret color and code word presented to the user in each pop-up window. Beyond adding new functionality to a user's browser, the NEX extension actively protects users from known scammers by forcing a redirect when it encounters a known malicious website. For a NEX token. The NEX token allows holders to claim a share of fees generated by the payment service and exchange. In total, 50 million tokens will be issued that entitle holders to a share of the fees taken by the exchange and payment service. NEX holders can claim their profits through a staking process, where claims on the staked NEX operate similar to gas claim calculations on the NEO network. In this way, token holders who stake NEX benefit directly from the success of the exchange services. As more fees are generated, holders will receive larger rewards. NEX tokens will be regulated as registered European securities with plans for expansion to other jurisdictions. 4.1 Calculating fees. Fees are calculated in terms of each asset traded or transferred on NEX. For example, if a user places a market price order trading 1000 NEX for NEO, then the exchange will collect a fee of 1000. 0.0025 equals 2.5 NEX. Similarly, if a user transfers 1000 NEO on the payment service for a fee of 0.001 gas, that fee will be added to the gas fee total. Total NEX fees are calculated by simply computing the fees taken for each asset on the exchange. As fees are taken, a proportion of them are moved to an independent smart contract that manages the claiming process. 10.4.2 Claiming fees via staking NEX tokens. Users can stake their NEX tokens in a smart contract that pays out a proportion of exchange and payment Service fees. To stake their tokens, users send their NEX tokens to the smart contract via a stake method that records the starting block and the amount sent by the user. The user can then make periodic claims on the contract to retrieve their share of NEX profits since staking began. Users can commit to staking their tokens for longer periods of time to receive a larger proportion of fees. The base rate of fee share will be 25%. If the user stakes their NEX tokens for 1 day, increasing linearly up to 75% if a user is willing to stake for 2 years for 1 claim. Example: a user owns 1,000 NEX, and NEX has generated fees in tokens equivalent to $100 million at market value since they last made a claim. Assuming the user has staked NEX at the 2-year staking rate of 75%, they would be eligible for a claim worth $100. 000 000 1050 000 0.75 equals $1,500. The claim can be received. The user claims a direct cut of fees across each token on the exchange. So if NEX is trading NEO, gas, NEX, and RPX, the user would receive a share of each of these assets. The user claims an equivalent amount in one preferred asset type. Here NEX will do the conversion automatically using its trade features and corresponding fee structure. 4.3 Token sale. NEX will hold a token sale in April of 2018. We plan to sell 25 million tokens to the public, of a total pool of 50 million. As payment methods we accept NEO and gas only. More details are available on our website, https://neonexchange.org. 5 Progress and Roadmap. Here we describe the current state of development on NEX. 5.1 Development. We have completed and deployed smart contract prototypes for trading and withdrawal features on the exchange. Development of the matching engine has begun and a full prototype will be available in early 2018. We have also released an alpha version of the NEX web extension, which will connect with the exchange for asset conversion, and begun work on the trading user interface. We have created and shared template code with our banking partners that will allow them to interface with the NEX extension to buy cryptocurrencies and send them to a user's account. 5.2 Partners. We'd like to thank our partners for their continuous support in legal matters. Brown Rudnick LLP, Nigel Rechtsenwald GmbH, Ernst & Young AG, Identity Mind Global, GN Truhand Establishment, and one undisclosed partner. 5.3 Incorporation. NEX is a limited company registered in Vaduz, Liechtenstein. Neon Exchange AG. We are currently cooperating with financial authorities in pursuit of acquiring an organized trading facility, OTF. License. 5.4 Roadmap. Q1 2018. Launch of web extension for DApp integration with Neo Blockchain and NEX Exchange. 11. Registration, lottery, and KYC for NEX token sale. Release of an open-source framework for conducting such sales, including smart contracts, wallet and extension integration, KYC, and backend website, open-source framework and template for interaction with NEX banking partner APIs. Announcement of partnerships. Q2 2018. Participation for lottery winners in the NEX token sale. Matching engine launch on Neo Testnet, along with V1 of Exchange APIs for testing with our liquidity creation partners. For example, trading bots, trading interface launch on Neo Testnet, usability research and information gathering from alpha testers. NEX web extension support for ETH and ERC20 tokens. Buy and sell Neo, gas, and RPX through banking partners. Release of V1 of web extension DApp APIs for integration on client websites and smart contracts on ETH and Neo. For example, APIs that allow websites to interact with smart contracts or request payments in Neo or ETH or constituent tokens from a user. Q3 2018. Beginning of trading operations. Matching engine and trading user interface launched on mainnet with support for Neo, ETH, NEP5, and ERC20 tokens. Cross-chain token conversion support in NEX extension wallet. Launch of staking contract on Neo for holders of NEX to receive exchange revenue. Q4 2018. Once required licenses are granted, NEX and other security token trading starts on NEX. Advanced trading features. Cross-chain support for trading BTC, LTC, and RPX on NEX references. 1. Cure 53 https://cure53.de. 2. coinmarketcap.com http://coinmarketcap.com. 2017. 3. EtherDelta https://etherdelta.com/access 2017. 4. Etheropt https://github.com/etheropt. Access 2017. 5. Maker Market https://osysdex.com. Access 2017. 6. Raiden Network https://raiden.network. Access 2017. 7. Why We Are Building Cardano https://ycardano.com. Access 2017. 8. Bitcoin Developer Guide. Proof of Work https://bitcoin.org and Developer Guide Proof of Work. Access 2017. Archived at https www.webcitation.org 6v7-9jj on November 20, 2017. 9. Bitcoin Developer Guide. Simplified Payment Verification https://bitcoin.org and Developer Guide Simplified Payment Verification SPV. Access 2017. Archived at https www.webcitation.org 6v7-9jj on November 20, 2017. 10. Bitcoin Developer Guide. UTXO https://bitcoin.org and Developer Guide Termuxo. Access 2017. Archived at https://www.webcitation.org 6v7-9jj on November 20, 2017. 12. 11. The Cost of Decentralization in 0x and Ether Delta http://hackingdistributed.com. August 13, 2017 Cost of Decent. Access 2017. Archived at http://www.webcitation.org 6v7ff8r7d on November 20, 2017. 12. Ethereum Wiki. Design Rationale https github.com Ethereum Wiki Design Rationale Accounts and not access. Access 2017. Archived at http://www.webcitation.org 6v7fswiki2 on November 20, 2017. 13. NeoNep 5. Token Standard https://github.com/neo. Project Proposals Blob MasterNet 5 Media Wiki. Access 2017. Archived at http://www.webcitation.org 6v7fuupv2 on November 20, 2017. 14. Ethereum Wiki. Proof of Stake https://github.com/ethereum/wiki/proof of stake frequently asked questions. Access 2017. Archived at http://www.webcitation.org 6v7g0yaqh on November 20, 2017. 15. CME Matching Algorithm. FIFO https://www.cmegrip.com/confluence/display Epic Sandbox Matching Plus Algorithms Matching Algorithms FIFO. Access 2017. Archived at http://www.webcitation.org 6v7grcz on November 20, 2017. 16. High Frequency Trading on the Coinbase Exchange https://www.coindesk.com/High Frequency Trading on the Coinbase Exchange. Access 2017. Archived at http://www.webcitation.org 6v7ghnihg on November 20, 2017. 17. Loopring White Paper https://github.com/loopring/whitepaper/blob/master/n-whitepaper PDF. Access 2017. Archived at http://www.webcitation.org 6v7new8z7 on November 20, 2017. 18. Atomic Swaps on the Lightning Network https://bitcoinmagazine.com/articles/Atomic Swaps How the Lightning Network Extends to Altcoins 1,484,157,052. Access 2018. archived at http://www.webcitation.org/6YEO5 back on March 27, 2018. 19. Lightning Network https://lightning.network access 2018 archived at http://www.webcitation.org/6YEXP on March 27, 2018. 20. Castro, M. Liskov, B. et al. Practical Byzantine Fault Tolerance, in OST, Volume 99, 1999, 173-186. 21. CoinDesk, The Bitfinex Bitcoin Hack, What We Know and Don't Know https://www.coindesk.com/Bitfinex Bitcoin Hack No Don't Know, 2016, archived at http://www.webcitation.org/6v7fw2mc9 on November 20, 2017. 22. Coleman, J. State Channels http://www.jeffcoleman.ca State Channels, access 2017, archived at http://www.webcitation.org/6v7f0gbq on November 20, 2017. 23. Herzog, E. Binartzi, G. and Binartzi, G. Bancor Protocol, a hierarchical monetary system and the foundation of a global decentralized autonomous exchange, 2017. 24. Liu, L. Chain Relays for Cross-Chain Trades https://blog.kyber.network/chain relays or a practical approach for cross-chain trades D0D7003F266B, access 2018, archived at http://www.webcitation.org/6v7ff8r70 on March 27, 2018. 25. Othman, A. Pennock, D. M. Reeves, D. M. and Sandholm, T. A practical liquidity-sensitive automated market maker, ACM Transactions on Economics and Computation 1. 3. 2013. 14. 26. Swan, M. Blockchain, Blueprint for a New Economy, O'Reilly Media, Inc., 2015. 27. Bucolic, M. The Quest for Scalable Blockchain Fabric, Proof of Work versus BFT Replication, in International Workshop on Open Problems in Network Security, Springer, 2015, 112-125, 28. Warren, W. and Bandili, A0X, An Open Protocol for Decentralized Exchange on the Ethereum Blockchain, 2017. 29. Wired Magazine, The Inside Story of Mt. Gox, Bitcoin's $460 million disaster https://www.wired.com/2014/bitcoin-exchange/2014, archived at http://www.webcitation.org/6v7fulqz on November 20, 2017. 30. Wood, G. Ethereum, a secure decentralized generalized transaction ledger, Ethereum Project Yellow Paper 151, 2014. 13. 31. Zhang, E. and Huangfei, D. Neo White Paper http://docs.neo.org and as index HTML, access 2017, archived at http://www.webcitation.org/6v7fguz on November 20, 2017.